Consider a graph that represents a social network where the vertices are the people and the edges represent some sort of interpersonal relation between them. For example, two people can be connected by an edge whenever they are acquaintances. Most such graphs which arise from real-world social networks have community structure. By community structure, we mean that the vertices can be partitioned into these clusters or communities such that the clusters are densely connected internally and vertices from different clusters are sparsely connected. What this means is that most of the edges of the graph connect vertices from the same cluster, whereas relatively fewer edges connect vertices from different clusters. One algorithm to find these communities or clusters in a graph is called the spectral clustering algorithm. It involves computing the Laplacian matrix of the graph and then using the eigenvectors to somehow find these clusters. At first glance, it's not clear why the algorithm should work. In this video, we'll try to rediscover the spectral clustering algorithm for ourselves. To make things simpler, let's start with the case where the graphs are unweighted and undirected and we want to partition the set of vertices into two clusters. Before actually trying to find these clusters, let's discuss what a good clustering even means. For example, here on screen we have two drawings of the same graph which partition the set of vertices into two clusters in two different ways. The clustering on the right is arguably the better one of the two. Let's discuss quantitatively what makes this clustering better. For the ease of discussion, let's call the clusters A and A complement. Such a partitioning of the vertices into two clusters is sometimes called a cut, and we want to quantify which cuts actually lead to good clusters. Now the reason as to why the left clustering is not a good clustering is that there are a lot of edges crossing from A to A complement, whereas the number of such edges is very low in the second clustering. Introducing some notation, the set of edges crossing from A to A complement is sometimes called the boundary of A and is represented by the partial operator followed by A. As we've already discussed, we want the boundary of our cut to be as small as possible. This is actually a good starting point, but the boundary can be small when one of the clusters itself is very small. So, instead of just trying to minimize the boundary of A, we somehow have to change our objective function so that it becomes larger when one of A or A complement is very small. There are a couple of ways to do this. The first one is called Cheeger's constant. In this case, our objective function h of A is defined as the size of the boundary of A divided by the size of the smaller of the two clusters A or A complement. H of G, also called the Cheeger's constant of the graph, is the minimum value of h of A over all possible clusterings of our graph into two clusters. Note that our objective function h also decreases when the boundary of A becomes smaller. However, when one of A or A complement becomes very small, the denominator is small and hence h of A itself is large. Note that minimizing h is actually a good way of finding good clusters. This is because when h is small, the boundary of A is automatically small and none of A or A complement are small enough. Another objective function which people study is called the conductance. For this, define the volume of A to be the sum of degrees of all vertices V in A. The degree of a vertex V is the number of edges that are incident on V. Volume is just a different measure of how large a set of vertices is. So we can define another metric phi of A for how good a clustering is, and phi of A is similar to h of A, but the sizes of A and A complement in the denominator are replaced by the volumes. So just like before, phi of A is small whenever the boundary of A is small. However, if one of A or A complement has very small volume, then phi of A would be large. Just like before, phi of G, called the conductance of the graph, is the minimum value of phi of A over all possible clusterings of the graph into two clusters. Now that we have reformulated our problem into these minimization problems, it should be easy to solve these, right? Well, the sad part is that finding the clusterings for which phi and h are minimized is a computationally hard problem. This means that there are no known algorithms which can minimize h or phi in reasonable time. The technical term here is NP-hard, but you can just ignore that if you don't know what that means. The main motivation for the algorithm comes from the following idea. Suppose you have a graph that can be partitioned into two clusters such that there are only a few edges passing between the two clusters. These edges form what is called a bottleneck in the graph. Now imagine something that can flow along the edges of this graph. This something, whatever it is, imagine it starts completely in the left cluster. Then since there are so few edges passing from the left cluster to the right cluster, this thing will take a long time to be present in both the clusters in equal quantities. An example of this thing which can flow across the edges is heat. For instance, suppose we heat up all the vertices in the left cluster. Then this heat will take a long time to reach the right cluster because there are so few edges that can carry this heat there. This tells us that if we can somehow find a temperature distribution that reaches stationary state very slowly on this graph, then perhaps we can reverse engineer these clusters out of that temperature distribution. With this in mind, let's take a quick detour and learn about the heat equation. This differential equation is called the heat equation. On the left hand side, we have the rate of change of temperature with respect to time. Notice that it is a partial derivative because temperature is a function of both position and time. On the right hand side, we have this positive constant alpha which depends on the medium in which the heat transfer process is taking place. The more interesting term on the right hand side is this triangle operator applied to the temperature function. This is called the Laplace operator and is defined as follows. The Laplace operator applied to f, also called the Laplacian of f, is the sum of the second order partial derivatives of f along all the coordinate directions. So for a function f which takes in a single real number as input, the Laplacian of f is just the second derivative of f. It is not immediately clear why the Laplacian of the temperature should appear on the right hand side in the heat equation. To build some intuition around this, let us see what the Laplacian of a function actually represents. Consider a function that takes in one real number as input and call it f. This is the graph for our function f. Now on this graph, consider the point corresponding to input x and two of its neighbors corresponding to inputs x minus epsilon and x plus epsilon. This distance right here is the difference in the function values at x minus epsilon and x, and similarly this distance is the difference in the function values at x and x plus epsilon. From the figure, we can clearly see that the first length is larger than the second length. You can pause the video and try to convince yourself that this will always be the case whenever the graph of the function f is concave upwards in our interval of interest. Rearranging the terms, we can read the same inequality as follows. The average value of f at the neighbors of x is larger than the value of f at x itself. We'll try and quantify the difference between the two sides of the inequality. Firstly, some notation. F subscript s represents the average value of the function f at all points which are at a distance epsilon from x. In the 1D case, there are only two such points, x minus epsilon and x plus epsilon. In the 2D case, we'll have to take the average value over all points on a circle, and in the 3D case, we'll have to take the average value over all points on the surface of a sphere. The quantity that we are interested in is this average value at the neighbors of x minus f of x. After a few simple manipulations, we get this term which just looks something like the second derivative of f. Indeed, as epsilon tends to 0, this number approaches the second derivative of f. In the one-dimensional case, the second derivative is the same as the Laplacian, so we replace this whole thing by the Laplacian of f. Notice that we have put the approximately equal to sign instead of the equal to sign because the quantity that we replaced by the Laplacian of f is actually exactly equal to the Laplacian only in the limit. The approximation here gets better and better as epsilon goes to 0. Now, although we have done this analysis for a function on the reals, A similar result also holds in n-dimensional space. On the right hand side in this general result, we have the error term which contains the powers of epsilon higher than 2. The key takeaway here is that the Laplacian of a function f at a point p tells us how large the value of the function in the neighborhood of p is on average when compared to the value of f at p itself. With this knowledge of the Laplacian, let's get back to the heat equation and see why the Laplacian makes an appearance there. Now, let's get back to the heat equation and see why the Laplacian of the temperature function appears on the right hand side of this equation. This is not the perfect physical analogy, but it does the job of explaining why the Laplacian appears pretty well. Suppose our medium in which the heat transfer process is taking place is made of these atoms, and all the atoms are at the same temperature except one which is cooler than the rest. First of all, each atom only knows about the atoms which it is in contact with. So the rate of change of temperature of any atom depends only on the neighborhood of that atom. If the neighborhood of an atom is hotter than the atom itself, or equivalently, the Laplacian of the temperature is positive, then the temperature of this atom should begin to rise because it will absorb heat from its neighbors. The rate at which its temperature will increase will depend on how hotter the neighboring atoms are. This is exactly what the heat equation tells us. The rate of change of temperature of a point depends on how hotter or colder the neighboring points are. The original motivation to study heat transfer was to somehow use it to find clusters in graphs. So let us now come back to the discrete case and build a model for heat transfer on graphs. There are two things to keep in mind. Firstly, we are discretizing both space and time. The space is now a graph and time will also move in discrete steps. Second, in our graph, the edges are what will carry the heat between vertices. Before building our model, let's outline a few basic assumptions. The first one tells us about how much heat will flow along an edge in a given time instant. As we have already mentioned, if there is no edge, there is no way to directly transfer heat between two vertices. On the other hand, if there is an edge between y and x, then the rate of heat transfer along that edge will be proportional to the temperature gradient across that edge. This agrees with our intuition because if the two endpoints of an edge are at similar temperatures, little to no heat will flow along the edge. However, if an edge connects a very hot vertex to a colder vertex, then the hot vertex will try and lose heat to the colder vertex rapidly along this edge. The second assumption outlines the rate of change of temperature of a certain vertex. Since time is discrete, the rate of change is actually a finite difference of the temperatures. This assumption states that the rate of change of temperature of the vertex x is proportional to the amount of heat it receives in a given time instant. Now, since heat can only flow along the edges, we can write the heat received by x as the sum of heat flowing along all edges which are incident on x. We are summing over all the vertices y which are adjacent to x. This notation will be used repeatedly throughout this video. Starting with the second assumption, on the right hand side we have the sum of heat flows along certain edges. Assumption 1 tells us that the heat flow along an edge is proportional to the temperature gradient across the edge, so we make this substitution. Now, the constants of proportionality for assumptions 1 and 2 depend on the conducting properties of the edges and vertices of the graph. However, for simplicity, we'll assume that the edges of the graph are all identical and the same holds for vertices. So we can assume a common constant of proportionality beta for our heat equation. Beta is actually a positive constant. We can distribute the summation and then in the second term, notice that the temperature of x is independent of the summation variable y, so we bring that out of the summation. The number of vertices y which are adjacent to x is just the degree of x. That way, we get the heat equation for the discrete case. Notice that the equation is linear in the temperatures of the vertices, so there has to be a more convenient way of writing the equation in matrix form. For a start, let the boldface T represent the vector of the temperatures of all vertices. We'll now introduce some common matrices associated with the graph. To start off, we have the adjacency matrix, in which the entry in row I and column j is 1 if I and j are adjacent and is 0 otherwise. The main reason for why this is useful to us is the following equality. On the left hand side, we have a sum over all vertices y adjacent to x, and on the right hand side, we have converted this into a sum over all vertices y. To see why the equality holds, just see that the right hand side term is 0 whenever y and x are not adjacent. This means that the only contribution is coming from the terms when y and x are adjacent, which is exactly the left hand side. The reason why we care is that a similar term appears in our heat equation where we are summing the temperatures of all y's which are adjacent to x. So we use the adjacency matrix to simplify the equation. This is the adjacency matrix for our graph. Now for the second term, we introduce a matrix called the degree matrix of a graph. In the degree matrix D, all the off-diagonal terms are 0 and the terms on the diagonal are just the degrees of the vertices. Using a similar argument, this lets us replace the second term in the heat equation by the following sum. To see why this is valid, just note that dxy is 0 whenever x and y are distinct. So the only contribution comes from the term when x and y are the same. And that term is just degree of x times the temperature of x, which is exactly what we wanted. This is already starting to look like a matrix product because the first term is the product of row x of matrix A with the temperature vector, and similarly the second term is the product of row x of matrix D with the temperature vector. Stacking the equations for all the rows together, we have this nice matrix form for the heat equation. Comparing with the continuous heat equation, in both the equations, we have the rate of change of temperature with respect to time. In the continuous equation, on the right hand side, we have the Laplacian of the temperature. In the discrete case, the matrix D minus A is multiplied by the temperature vector. It shouldn't come as a surprise if I tell you that the matrix D minus A is called the Laplacian matrix of the graph. The letter L is used to denote the Laplacian matrix. Note that the degree matrix as well as the adjacency matrix are symmetric, and so the Laplacian matrix is also symmetric. This will be useful later on. The Laplace operator tells us how different the value of a function is in the neighborhood of a point compared to the value of the function at that point itself. We expect the Laplacian matrix to play a similar role in the discrete case. Consider a function f that maps every vertex of our graph to a real number, and the column vector f collects the function values for all of the vertices. So essentially, for a graph, column vectors and functions are the same thing. When we multiply the Laplacian matrix by the function vector f, we get another vector, and we can interpret this as a function as well. The function associated with L times f maps the vertex v to this real number right here. We now do the exact same calculation that we have just done, but in reverse. On the right hand side, we have a measure of how different the values of the function are at the neighbors of v when compared to the value at v itself. Thus, in essence, the Laplacian matrix does in the discrete case what the Laplace operator does in the continuous case. Now that we have our heat equation for the discrete case, let's try and find the solution. The way I like to read the heat equation is as follows. Suppose I have the temperatures of all the vertices at the present time and I want to find the temperature vector at the next time instant. To do this, just take the matrix I minus beta L and multiply this by the current temperature vector. In general, suppose we are starting with the initial temperature vector T0. To find the temperature vector at time t, we just repeat this process t times. This is already some progress, and we now look for temperature distributions T0 that will give rise to nice solutions. The first natural place to look is the eigenvectors of L. So let vi's be the eigenvectors for L, with lambda i's being the corresponding eigenvalues. Without loss of generality, we can assume the following ordering on the lambda i's. So if the initial condition T0 is the same as an eigenvector Vk, we can find T1 as follows by noticing the fact that L times Vk is just lambda k Vk. What this means is that in moving from time step 0 to time step 1, the temperatures of all vertices got multiplied by this constant 1 minus beta lambda k. Again, if we want the temperature at time t, we can multiply by this number t times. Already with this much background and a bit of intuition about heat flow, we can prove a lot of interesting results about the Laplacian matrix. For a start, we can prove that all the eigenvalues are non-negative. To see this, note that if the initial condition is the eigenvector Vk, then our solution is as follows. If lambda k is negative, then the term in the brackets is more than 1 because beta is positive. This means that the temperatures of the vertices keep increasing in magnitude as time goes on. However, this clearly defies our intuition for heat flow. We expect the temperatures to settle to some finite value after a long time. So lambda k indeed is non-negative. The second claim is that the smallest eigenvalue lambda 1 is equal to 0. To see this, consider the initial condition where all the temperatures are the same. The heat equation can tell the temperature distribution at time 1, but since the temperatures are already the same, T1 is actually equal to T0. Doing some algebraic manipulations, we can write L times T0 is equal to 0. This means that T0 is actually an eigenvector of L and the corresponding eigenvalue is 0. So we know that all the eigenvalues are non-negative and there is at least one eigenvalue that is 0. Based on the ordering that we have assumed, we can say that lambda 1 is in fact 0. The corresponding eigenvector V1 is the all ones vector. The third claim is slightly more non-trivial. We claim that lambda 2 is positive if and only if the graph is connected, and otherwise lambda 2 is 0. In general, the multiplicity of the eigenvalue 0 is the same as the number of connected components in our graph. I'll leave this as an exercise. For a hint, the multiplicity of the eigenvalue 0 is just the number of orthogonal initial conditions that are actually already in stationary state. For a connected graph, there is only one such initial condition, the one where the temperature of all the vertices is the same. We look at the solution for the case when the initial condition is an eigenvector once again. Here the temperatures of the vertices vary in a geometric progression. The common ratio is 1 minus beta lambda k. Since we have proved that all the eigenvalues are non-negative, the common ratio is always less than 1. We'll assume that beta is small enough so that the common ratio is also positive. This means that the common ratio is between 0 and 1 for all the eigenvectors. So if the eigenvalue is 0, our temperature distribution is already at stationary state because the common ratio is 1. However, if the eigenvalue is strictly positive, then at infinite time, the temperature vector is close to the 0 vector. The rate at which the temperature vector approaches the 0 vector is determined by the eigenvalue. The larger the eigenvalue is, the faster it decays to the 0 vector. Note that here we are ignoring the case when lambda is equal to 0 because we have already handled that separately. To see this in action, consider two copies of our graph and the initial conditions are set according to the eigenvectors v2 and v5. the corresponding eigenvalues are 2 and 5. After a long time, the temperatures of the vertices in both the cases are close to 0. However, the rate at which the temperatures fall is higher in the case of V5 than in the case of V2. If our graph is connected, we can claim that the slowest mixing eigenvector is actually V2. This is because λ1 is 0, so V1 is already at stationary state, and among the positive eigenvalues, λ2 is the smallest, which implies V2 reaches stationary state in the slowest possible way. Enough about eigenvectors. Now we start discussing about the general initial condition. Luckily, our matrix L is symmetric, so we can write every possible vector as a linear combination of the eigenvectors of L. This is a consequence of the spectral theorem for symmetric matrices. In the interest of time, I won't go into the details, but the important part for us is that we can always write any initial condition as a linear combination of these eigenvectors. Since the heat equation is linear, the solution is also a similar linear combination of our original solutions. This means that the long-term behavior is dominated by the slowest mixing eigenvector, which in the case of connected graphs is V2. For an arbitrary initial temperature distribution, the higher the coefficient of V2 in the linear decomposition, the slower it will reach stationary state. So V2 is not just the slowest mixing eigenvector, it is actually the slowest mixing temperature distribution on connected graphs. The rate at which it reaches stationary state is determined by λ2. If λ2 is small, it reaches stationarity slowly, whereas if λ2 is large, even the slowest mixing temperature distribution V2 mixes relatively quickly. We can conclude by saying that if λ2 is large, the clusters won't be that good. This is because even the slowest mixing temperature distribution mixes relatively quickly. So there is no bottleneck for heat flow in our graph. On the other hand, if λ2 is small, then V2 reaches stationary state slowly, and we can hope to find some good clusters out of this slow mixing temperature distribution. For this reason, λ2 is often called the algebraic connectivity of the graph. If λ2 is small, the graph is not well connected in the sense that heat has trouble flowing between some regions of the graph. As already discussed, vectors can be reinterpreted as functions which map the vertices of the graph to real numbers. We interpret the vector v2 as a function. This gives us an embedding of our graph on the real number line. Now here comes one of the more important claims. If λ2 is small enough and we can actually expect to find good clusters in the graph, then under this embedding, for most edges, the two endpoints are mapped to closer real numbers. There are two ways to see this. The first one is an algebraic way, and the second one is through our heat transfer analogy. Note that this particular embedding is special in another way because it solves a certain minimization problem. Here, we are trying to put all the vertices of a graph on the real line and trying to minimize the sum of squared edge lengths. The constraints are so that we don't get the trivial solutions where all the vertices are mapped to the same point. Again, we won't go into the details, but for a hint, this expression is actually equal to x transpose Lx. The minimum value is actually λ2. So if λ2 is small, this means that we have actually succeeded, because most edges connect vertices that are close together in this embedding. In other words, very few edges are stretched out to long distances on this number line. Let us see how this fits with the heat picture. If two vertices have vastly different temperatures, then heat would flow quickly between them. If there are many such edges, then a lot of heat would flow through too many edges and the slow mixing temperature distribution will not survive. Putting the vertices on a real number line according to scale, we can say that the vertices that end up close together on this real number line are tightly connected in the graph itself. By tightly connected, we mean that most of the edges of the graph connect vertices which are close together in this embedding. So we can just cluster the vertices based on these function values. Clustering based on these function values means that the numbers that are close together tend to lie in the same cluster, and the numbers that are far away tend to lie in separate clusters. Note that this is exactly what we want with our community structure clustering. Vertices from the same cluster should have more edges between them, and vertices from different clusters should have fewer edges. Since we have already discussed how being close in this embedding actually translates to more chances of having an edge between the vertices, we can see that clustering based on this embedding actually makes sense. Clustering real numbers is arguably easier than clustering vertices in a graph. We can just choose a threshold, and every number larger than that threshold is one cluster, and every number smaller than that threshold is another cluster. Looking at the picture, this is a decent clustering of the real numbers into two clusters. The corresponding clustering for our graph is shown in this picture. Let us try and write down the algorithm formally. Firstly, we compute the eigenvectors and eigenvalues of the Laplacian matrix associated with our graph. Note that here we are assuming that the graph is connected. If the graph is disconnected, then we already have the components as some clusters, and then we can use the clustering algorithms on these connected components separately. After we compute the eigenvectors and the eigenvalues of the Laplacian, we use the eigenvector corresponding to the second smallest eigenvalue to get a real feature value for each node. This is the embedding of the vertices on the real line that we have just discussed. Now that we have these feature values, we can cluster the nodes based on these feature values alone. This algorithm is specifically for the case when we want two clusters. We'll discuss the general case later in the video. There are some variants of the algorithm where we use matrices other than the Laplacian matrix. We can use one of the three normalized Laplacian matrices. The first one is the left normalized Laplacian matrix, and this is equal to D inverse times L. Similarly, we have a right normalized Laplacian matrix, which is equal to L times D inverse. The symmetric normalized Laplacian matrix, or just the normalized Laplacian matrix, is defined as follows and is a symmetric matrix. The eigenvalues for all of these matrices are the same. In practice, the symmetric normalized Laplacian is used often. For some bounds, let lambda i's be the eigenvalues of the Laplacian matrix and mu i's be the eigenvalues of the normalized Laplacian matrix. Then we have the following inequalities. In the first one, the Cheeger's constant of the graph h of g is bounded both above and below by functions of lambda 2. Loosely speaking, this means that the Cheeger's constant is small if and only if lambda 2 is small. Similarly, the second eigenvalue of the normalized Laplacian is associated with the conductance of the graph. The conductance is bounded both above and below by these functions of mu2, and again loosely speaking, phi of g is small if and only if mu2 is small. Just like all the algebraic results in this video, we won't be proving this one either. This is just to show that there are actual theoretical results which can formalize our hand-wavy statements. For a long time now, we have been saying that lambda 2 is small if and only if we can find good clusters in our graph. In the beginning of the video, we said that h of g and phi of g are small whenever we can find good clusters in our graph. What these inequalities tell us is that the second eigenvalue of these matrices is small if and only if one of the objective functions is small. The objective function being small guarantees that there is actually a good clustering in our graph. In summary, you have good clusters if and only if the algebraic connectivity of our graph is small. A similar result can also be stated for the normalized Laplacian matrix. Let us try and generalize our algorithm so that it will work when we want 3 clusters in our graph. So again, the first step, just like before, is to embed the graph on a real line based on the values of the vector v2. In this case, 2 natural clusters already appear, but we want 3 clusters. One way of doing this might be to use the same algorithm on the subgraphs induced by the clusters recursively. However, there's a cleaner way to do this. Right now, we have separated the vertices in a single direction based on the values of the vector v2. Remember that v2 is actually the slowest mixing temperature distribution on this graph. If we actually have to give a runner-up award, we'll have to award it to the vector v3. So, using the exact same line of thought as before, we separate the vertices along the y direction based on the values of the vector v3. This is an embedding of the graph in 2-dimensional space. Now we can cluster these by looking at these as points in 2D space instead of vertices of a graph. Just like before, this embedding is also the solution to a particular minimization problem, one that again minimizes the sum of the squared lengths of edges. The picture that we have on screen is actually a pretty good drawing of the graph. This is because the objective function forces most of the edges to be of small length. This algorithm is a part of a family of algorithms to draw graphs, which is called spectral layout. In our particular example at hand, we have mapped the vertex A to the x coordinate dictated by v2 and the y coordinate dictated by v3. Spectral clustering can also be used to cluster points in space. Now you might be wondering that there is no graph to which to apply the algorithm. The key here is to construct a graph that captures the geometric information about the points. We define a similarity function which takes in pairs of points and outputs a real number. The similarity of 2 points decreases rapidly as the distance between them grows. This gives us a natural graph where these points become the vertices and the edges are weighted where the weights are the values of the similarity function. In case of weighted graphs, the adjacency matrix contains the weights of the edges rather than zeros and ones, and similarly the degree matrix contains zeros in the off-diagonal positions, and on the diagonal it contains the sum of weights of all edges incident on a vertex. Now we can use our usual spectral clustering algorithm to find clusters, and it actually performs pretty well on many datasets. For the people who made it till this point, here is a drawing of a graph that was generated using the spectral layout method which was already described. Thank you for being patient and listening to me. If you enjoyed the video, please engage with the video as well as the channel.